Hello everyone, I'm Norman Wahlberger. In this, the fourth of our string of videos on the most important and fundamental problem in mathematics, namely how to model the continuum, we tackle the main issue in this subject, which is the difficulties with the current theory of real numbers and the opportunities and challenges involved in moving beyond the current misunderstandings to a more effective and careful and coherent theory of the continuum based on a more solid understanding of computational issues. So we're going to be looking at different models of the real numbers today, in particular heading towards Dedekind cuts. And then we'll talk about the computational problems that are intertwined with essentially all of these different approaches to the real numbers. So this video is very much at odds with the majority thinking in 2014 with regards to the foundations of analysis. And I don't want to minimize the divergence between what I'm telling you here and what you will hear from most professional pure mathematicians. I would really like to encourage a wider and more involved and somewhat more serious discussion on this very important topic. It's something that I believe mathematicians have shied away from, partly because they don't really want to acknowledge the logical difficulties that are pretty clearly visible to anybody who looks at this topic seriously. All right, so we've talked a little bit about the history of attempts at understanding the continuum, the challenges that arose in the 17th, 18th, 19th centuries, driven largely by developments in the calculus. And we saw that in the 18th and 19th centuries, there were certain attacks on the foundations of calculus, which led people to start asking, well, how can we solidify our understanding of what the continuum and the number line really is? And the natural question, which probably occurs to many of you, is, well, why don't we just use Stevin's approach to decimal numbers, but suitably extend this to so-called infinite decimals? So not just to the repeating decimals like 8/11 equals 0.727272 and so on that Stevin was aware of, but also to other irrational numbers. For example, root 2, 1.414213562237 and so on, or maybe pi, 3.141592665 and so on, or maybe e, 2.71828182884 and so on, or maybe log 2, 0.693147180 and so on, or maybe an integral like the integral from 0 to 1 of dx over 1 plus x cubed, which evaluates to 0.835648848 and so on. So what we'd like is a theory of real numbers or irrational numbers in which these kinds of objects were completely clearly defined. So we knew exactly what the framework is to support an arithmetic with these kinds of objects. That was what was required. That was the challenge that 19th century mathematicians faced. How to go from Stevin's understanding of periodic fractions to a systematic, concrete, and logically correct theory of irrational numbers, including these ones and other ones. So this turns out to be a huge challenge, which, frankly, the 19th and 20th centuries were incapable of meeting. Now, if you weren't familiar with the different approaches that people took to establishing a theory of irrational numbers, you'd probably naively say, well, what's wrong with just extending Stevin's approach? Just working with infinite decimals, assuming this makes sense, because it's so in line with what the physicists and the engineers are actually working with. Engineers and physicists are always working with essentially decimal numbers, and they don't need anything beyond that. So it makes sense to try to establish a theory of irrational numbers from the point of view of Stevin's framework. Sadly, this does not work. And that's the reason why you do not see such a theory developed in any of the standard calculus texts, nor in any of the standard analysis texts. If such a theory did work, then it would surely be presented in those places, because then there would be a clear foundation for the theory of real numbers. Okay. But there's a reason why such an approach is not taken. And we can see it reasonably clearly in say, an example. So let's suppose, for the sake of argument, that there really is something called pi, and that it consists of some infinite string of digits starting with 3.1415 and so on. And that there really is an object called e, which starts 2.71828 and so on, and carries on in some fashion, which we could, in principle, enunciate, at least to carry on developing more and more digits. All right, now let's ask ourselves, how would we multiply two such infinite decimals? Well, it's obvious that Stevin's framework doesn't really apply for the same reasons that I outlined last time, that Stevin's approach is to take such decimals and start at the right and work your way from the right to the left. The problem with that clearly is that there is no right endpoint to these numbers, and so we're not in a position to do what Stevin told us to do in terms of the arithmetic of decimal numbers. We must proceed in a different way. We must proceed really from the left and work our way to the right, exactly the opposite of what Stevin suggests. There's really no other way of doing things. So we're going to start by multiplying 3.14 and so on by this 2. And then we're going to multiply it by the 0.7 and then by the 0.01. And each one of those operations we're also going to have to start from the left. So when we multiply this thing by 2, we're going to have to start on the left because it's all what we can do. And we're going to work our way to the right and make adjustments as required. Whenever there's a carry, we may have to rub off and change one of the entries that we already have. So let's see how that would go. Let's try. So 2 times 3.1415, etc. 2 times 3 is 6. 2 times 1 is 2. 2 times 4 is 8. So far, so good. 2 times 1 is 2. Okay, so we would write a 2 there. And then at the next stage, we would have 2 times 5 is 10. So we would have to put a 0 here and then carry a 1. And that means that that 2 that we wrote down would have to be rubbed off and made a 3. So I've just written the 3. And now there's at this point a 0 here. And you can see, all right, we should be a little bit tentative about putting a 0 here, but you have to actually look at the next one. 2 times 9 is 18. And so there's going to be a carry there, so that 0 turns into a 1. So we have to proceed along in this direction, and eventually we get to the limits. I happen to have stopped the decimal at that point there, and so that next thing there is ambiguous. We don't really know what that thing is because we need more information to determine it. Okay, then we can write down the same kind of thing, multiplying this by 0.7. The 7 times 3 is the 21, and the 7 times 1 is a 7, but then the next one is 7 times 4, which is 28, and so that will bring the 7 up to a 9, and there'll be an 8 there. And in such a similar way, we can calculate that this thing times 0.7 is a decimal that at least starts this way, and eventually it becomes a question mark because we need to know more information. All right, so we can keep doing this. We can multiply by 0.01, and then 0.008, and then there's a 2. This one will look a lot like the one we just did up here, except it'll be over a couple of digits. And then another 8, which should be the same as this one. We're going to have this series of multiplications, for each one of these. And then the job is to add them all up, as we do in ordinary multiplication. But here the task is complicated by the fact that, in fact, there are an infinite number of such rows to add up. Fortunately, the elements, the non-zero elements in these rows are staggered ever more to the right, so that any one column has only a finite number of non-zero entries. So even though there are, in fact, an infinite number of rows. Any one column, you look above it, there's mostly zeros, and then there's only a finite string. But nevertheless, we do have the problem of carries. So 6 plus 2 is 8. 2 plus 1 is 3. Why is there not a 3 here? Well, because the next column, there will be something that will carry. 8 plus 9 is 17, plus 3 is 20, plus 2 is 22. So there will be a 2 here, and carry the 2 makes that 3 into a 5. But we can't really write 2 down here because we have to worry about the next column first. And the next column is, I guess there's 10, 18, 24. So we put a 4 there and make it 2. The 2 becomes a 4. And then this, what did I say there was going to be here? I think it was a 4. And then when add the next column, we get 6, 7, 8, 9, 10, 11. All right, so there'll be a 1 there and then a 1 carried to make that a 5. And as we keep doing this, the column sums will of course get larger and larger. And the carries will not just be affecting the previous entry, but they'll at some point start affecting the previous entry and the one before it. And once we get into the, a million places over, then the entries of every column will be spilling over quite a lot of the earlier entries. So you can see that this is very challenging. Okay, to write down exactly how one does such a multiplication is not at all clear. So even the definitions of the operations at the level of infinite decimals is not at all clear how to define them. And then it's not at all clear what happens when you try to take those laws of arithmetic, assuming you're able to define them properly, and then prove that the laws of arithmetic, like the commutative law, associative law, distributive laws, that they work. Okay, so these days, when people talk about the product of pi times e, there's never an understanding that we're forced to make a calculation like this. If we were talking about finite decimals, yes, we would be obliged to actually make the calculation. There would be no way of avoiding it. We couldn't pull a get out of jail free card out of our back pockets and say, oh, we don't have to do it. If I asked you to multiply those two finite decimals, you'd have no choice but to go through something like this and make the calculation and actually write it down. But with infinite decimals, the whole thing is so complicated and ultimately somehow dissolves in a kind of a murk of ambiguity that we resort to something like this. We say pi times e. If you ask a modern mathematician, what is pi times e? They'll tell you, well, it's just pi times e. This is what we do because this kind of arithmetic is too onerous, too fraught with difficulties, both operational and theoretical. So if you're a keen high school student, you may have watched that and said, yeah, okay, there's technical difficulties here, but I can imagine I could be careful and surmount them. And perhaps you could. Perhaps you could say exactly how to multiply two infinite decimals, and perhaps you could prove the associative law of multiplication for them. So the technical difficulties are there. But the more serious problem is that there are insurmountable logical difficulties as well. Okay, so let's see what they are. And this can be illustrated just by operation of addition. So here is one infinite decimal, and here's another one, and they're not any particular infinite decimals, they're just some random ones. Let us see how we add them. All right. So we know that there's only the possibility really of starting at the left. So we start at the left here, and there's a 0 here and a 1 here, so we want to put a 1 here, but we see that this 5 plus 6 is going to be an 11, which is going to spill over. So that's going to be a 2. And before we put a 1 here, we look at the next column, we see there's a 4 plus 3, which will be a 7, which will not spill over. So we're confident we can put 21 there. All right, so this 7 is okay because the next one's going to be a 5. Okay, this next one being a 5, well, we can't put it quite there because the next one is going to be 2 plus 8, which is 10, which is going to spill over, carry. So the 5 that we wanted to put there has to be augmented with a 6. So far, so good. All right, the 0 that we got here has to be, well, we have to check 2 plus 3. That's not going to spill over, so all right, we're okay to put a 0 there. The 2 plus 3, we'd like to put a 5 there, and then we check the next one. 4 plus 5, well, that's a 9. Can we write a 5 there? There's a 9 following. We have to be a little bit careful now because that 9 has the potential to spill over into a 10. If there's a carry from the next column, then that 9 will kick over to a 10, and that will kick a carry from this column over to this one, and that 5 will change to a 6. So we cannot evaluate this fellow before we not only look at this column, but also at the following column. The following column is also sums up to a 9. So in fact, the same thing holds. We're not sure what's happening at this column because we have to go to the next column. When we do go to the next column, we see a 2 plus 8, which is a 10. At that point, we know there's going to be a 1 carry, which will kick this 9 to be a 10, which will add a carry to that, will kick that 9 up to be a 10, and so there will be a 1 coming there, and we know that's going to be a 6. And then that's going to be a 0. And that's going to be a 0. And this 2 plus 8 was a 10, so there was a 0. And then the next column is telling us that there's not going to be a carry, so we can be sure there's going to be a 0 there as well. So we had this string of 9s, but we were able to surmount the difficulty by just keeping track of the 9s and going to the end of where the 9s stopped and then seeing what happened, seeing if there was going to be a carry that would spill over sequentially through all those 9s to the place before the 9s began. All right, let's keep going a little bit further. It's going to be a new challenge coming up ahead. Okay, 1 plus 1 is 2. There's no carry to the next one. That's going to be 2. 0 plus 0 is 0 for sure. 0 plus 0 is 0, but now there's a possibility of a carry because there's a 4 plus 5, which adds up to 9. The following one we have to check. That's 3 plus 6. That's also 9. Okay, we have to go one more. We're still trying to work out this one here. That's 9. That's 9. So we have to look at the next one to see if there's a carry that will spill over. That happens to be 9 as well. Okay. Then the next one is 8 plus 1. That's also a 9. A little bit annoying. Then 8 plus 1 is another 9. And then there's a 4 plus 5. That's another 9. The string of 9s that I've gotten here prevents me from writing down this one here. I want to write the next digit here. But the string of 9s that are being summed up here prevents me from doing that. I need to go further. Okay, now here's where the problem is. Suppose I go further. And suppose I notice that for the next 200 digits, the sum of the entry in the top number and the bottom number is always 9. They're always different, or they're possibly different, sometimes the same, but they're always adding up to 9. 200 places. That means I can't write down the value of this one until I've gone past those 200 9s added up. Now suppose that instead of having 200 places, I had 200 billion places. Suppose that these real numbers are sort of conspiring against us, so that there are 200 billion 9s being produced when we add up these digits. That means we have to trail through all of those, searching and searching for a non-9. And when we finally get one, then it'll either be a carry, which will go through the whole sequence and affect this one, change it from a 0 to a 1, or there will not be a carry, in which case we will be confident to be able to write down a 0 there. So we've gone 200 places. We still have not found a place where this one and this one add up to something different from 9. We're starting to get frustrated. We're starting to think there's a conspiracy here. This is not just bad luck. Whoever has given us these two real numbers is out to make our job hard. And at some point we have to address the possibility that maybe this string of 9s, the string of 9s that we get by adding these two things together, carries on indefinitely. That it doesn't stop. And so our search for a non-9 is going to be a fruitless search. We are never going to find a non-9. We're just going to have to keep on going and going and going and going. And we will never be in a position of determining what this digit is. That means that in this case, we are incapable of writing down a rule which determines this particular digit of the addition of those two infinite decimals. There's nothing really we can do about it. So you might say, well, can't we look at the rule or the algorithm that generates these two sequences and examine them and see if there's some reason why these things seem to be adding up to 9s? Unfortunately, the framework that we're considering does not require these infinite decimals to be given by rules or by algorithms. We're allowing them to be arbitrary. So that means there's no way of looking behind these sequences to find a rule or an algorithm or a program that's generating them. We're just incapable of defining a rule of addition that for sure always works to create the sum of any given two infinite decimals. So in other words, arithmetic with these objects, with these infinite decimals, is actually impossible. It's logically impossible because of exactly this problem. Now you might say, well, wait a minute, so the problem is with this arbitrary, infinite aspect that there's no rules that generate these digits. And then I have to, unfortunately, tell you about the axiom of choice, which is a religious position that modern mathematicians generally accept, which is that arbitrary infinite decimal sequences do in fact exist. It does make sense to talk about infinite decimals which are not given by a rule, an algorithm, or a procedure. This is a particularly popular position that was developed in the 20th century, somewhat before computers really started getting going. These days, most people who have been trained with some computing abilities and orientation look more skeptically at such a claim. They would say, well, what do you mean by an infinite decimal sequence if there's no computer program ultimately to generate them? But nevertheless, the majority of mathematicians these days in the year 2014 believes in the validity of this particular axiom, and therefore they believe in the existence of infinite decimal sequences which are not given by rules, and so it follows as a consequence that arithmetic with such objects is not properly defined. It's a logical conundrum that you cannot avoid. So it's more than just a technical difficulty, it's a logical conundrum that prevents a proper theory of arithmetic with infinite decimals to be laid out. Which is the reason why you find such a thing never laid out. That's the reason why calculus books do not start with chapter 1 explaining the theory of real numbers in the context of infinite decimals. Because it does not work. I am sorry. Now, because I have no sympathy at all with the axiom of choice, and I think it's just gobbledygook, that objection is not really one that weighs heavily with me, because I don't accept that this underlying assumption is a valid one to begin with. For me, the real difficulty with the setup of infinite decimal arithmetic has to do with the nature of the infinite aspect of the decimals in the first place. Right. So the infinite aspect of Stebbins' nested sequence of decimal intervals is to me the primary problem. So let me remind you what Stebbins' approach is. Okay, if we have something like square root of 19, which ostensibly is this infinite decimal, 4.358898 and so on. What is Stebbins saying here? What does this mean? Well, it means that when we try to compute square root of 19, we have a procedure or an algorithm for doing it. And there are different algorithms, so you choose one. And then you start computing, and the first thing you find is that this number, whatever it is, has to be in the range between 4 and 5. So it has to be between 4 and 5. That's what this first decimal is doing. And then Stebbins says, all right, let's take this interval between 4 and 5 and let's blow it up. Let's magnify it so we can see it better and subdivide it into 10. 4.1, 4.2, 4.3, 4.4, and so on. And then we perform the algorithm and find that the square root of 19 has to be between 4.3 and 4.4. That's telling us that the second digit is a 3. And then we blow up that interval. There it is there, 4.3 to 4.4, subdivide into 10, run the algorithm, find out that the square root has to be between 4.35 and 4.36, which allows us to write the next decimal. Okay, so this is an algorithm, something that you do one step at a time. Every digit that you write down corresponds to another step that you have performed. Okay, so my objection to the idea of this as an infinite decimal is that it implies that you have evaluated this procedure an infinite number of times. And to me, that just doesn't make sense, because it's not something that I can do. It's something that I'm confident that you cannot do. It's something that I'm confident nobody can do. Nobody can run this algorithm infinitely often. I'm happy to be convinced otherwise. I'm happy for somebody to do it and then to show us. But I'm pretty sure that that will not happen. So this, to me, is the essence of the objection. All right? That I'm claiming that when you think about an infinite decimal as something that really goes on infinitely, you are exceeding your capabilities as a human being and putting yourself at the level of God by claiming that you can do something which you in fact demonstrably cannot do. So this goes against my understanding of what mathematics is. In mathematics, we want to be honest. We want to be really honest. Yes. Here's one possible way of thinking about, the silliness of thinking that you can actually complete this sequence of operations. Suppose you actually believe this is a truly infinite object. Do you really think that it's possible to think about the whole thing going on infinitely beyond the end of time? So one thing you can do is pair these digits up 2 at a time, and then replace every pair with a suitable element on your computer keyboard. All right? So maybe there's roughly 100 different keys there, including capitals. So just line them up with these pairs of digits, including the space, so that then you can convert a sequence like this of digits to a sequence of strokes on your keyboard. That means you could read it. Okay? It's amusing to think about it that way. So that means if you read it, well, most of the time it'll be gobbledygook. But every so often you're going to see your name, Norman. The letters Norman will appear as we're reading this thing. Okay. But moreover, at some point, we are going to, assuming this number is normal, which is what most people believe, every so often we're going to come across a string, which is not just my name, but in fact my life story. My entire life story. My entire life story in all detail. Eventually I'm going to be reading all kinds of gobbledygook, and then there'll be a situation where the string starts to read, and here's Norman Wildberger's life story. Norman Wildberger was born, and then we'll give me the exact date, the exact time, at the exact place, the exact names of my parents, and then a complete story, a complete history of everything that ever happened to me in my life. When he was 13 years old, on his birthday, he went to the following movie and had ice cream at the following store and had the following conversation with his sisters and so on. Okay? An entire, completely accurate life story of my entire life story. That will be there somewhere in the decimal expansion of root 19 converted into typeface. But that's not all, my friends. Okay. A little bit further on, probably, you will find not just a history of Norman Wildberger, but an entire history of the universe. Okay? So at some point, you will start reading, and here is a complete representation of the history of the universe, where we catalog the position and velocities and momenta and who knows what of all particles throughout the entire history of the universe. So every little quark, all the little quarks at the end of this pointer, their positions will be recorded in this monumental treatise to exact accuracy. The entire history of the world, not just of the planet Earth, but all those distant stars, all those distant galaxies, every little quark, everything completely laid out. That's simply a consequence of the normality of this thing. Every true statement will eventually find its expression somewhere in here. Okay. The ridiculousness of this kind of discussion, I mean, it's clear that we've gone beyond mathematics, haven't we? Right? We are now talking about philosophy and some amusing thing that you have a cocktail conversation in, after a few drinks. This is not mathematics. The idea of this thing carrying on infinitely is, to my mind, pure and utter philosophy, if not religion. It ought to play no role in mathematics. So the logical difficulties that I laid out for Stebbins decimal numbers as a framework for doing infinite decimals or introducing irrationals became generally known. There may not have been a lot of discussion about it, but in the 19th century, people started becoming aware that there were problems. There were difficulties in laying out what exactly irrational numbers were and how we do arithmetic with them. And so people started looking for alternative ways of setting up the framework. And there were quite a few different alternatives proposed, and I want to run through a few of them, finishing off with Dedekind cuts. Okay, so the first variant, so this is an alternative to Stebbins' framework, is to think not about infinite decimals, but about arbitrary nested intervals. So we can interpret Stebbins' decimal numbers as being a bunch of nested intervals. The first interval is between 4 and 5. The next interval is between 4.3 and 4.4, and so on. But it's possible to be more general, to not insist that all of the intervals correspond exactly to a decimal subdivision of the previous one. Right? So we can be more general and just say, all right, let's consider an interval I sub 1 with endpoints A1 and B1. And inside that, we'll have a second interval, say I sub 2, with endpoints A2, B2. And inside that, a third interval, I sub 3, interval A3, B3, and so on. And the only thing that we really require from this string of intervals is that the length of the intervals should go to 0. They should become smaller and smaller. That's the critical thing. Okay, so we imagine this on the number line like this. So here's the first interval, we're calling I sub 1. And then inside here somewhere is a second interval, I sub 2. And inside that is a third interval, I sub 3. Inside that's a fourth interval. Inside that's a fifth interval, and so on. And as long as we insist that those intervals keep on getting smaller and smaller, approaching 0, then we can think about that whole conglomeration as being a real number. It's another way of thinking about what a real number is. It's a somewhat more flexible way than Stebbins, but still sort of in the same general direction. So such a datum is now a real number. So one of the advantages of this approach is that having freed yourself from the decimal framework, it corresponds more to certain operations that we do in analysis, or that we would like to do in analysis, where we're making certain limiting procedures, perhaps with integrals, maybe involved in lengths or areas, where we have a first bound, maybe even going back to Archimedes, for example, the area of a circle. Interior polygon, exterior polygon, calculating areas, and then you've got some interval. And then at the next stage, you make a more refined approximation of interior and exterior polygons. You get a smaller interval contained inside. And then you think about the area as being that whole collection of nested intervals. A disadvantage of this approach is that the uniqueness that we have with the Stebbin system is lost. So with Stebbin system, you end up with a decimal, 3.1415, so that the actual intervals are unique. There's no flexibility about them. Here we do not have any more unique representatives. We have to start talking about two different interval systems as being the same if they overlap at every stage. That's the essential notion of equality between such things. And it becomes much more challenging then to decide when two real numbers are actually equal. It becomes potentially quite challenging to decide whether our two real numbers are actually the same or not. This is a key point in setting up arithmetic. You have to be able to know whether two of your numbers are actually the same if you want to have any kind of sensible arithmetic. It also turns out that with the arithmetical operations, okay, addition is not too bad to get a hold of. The other operations are a little bit more problematic to set up. Another variant, closely related to the previous one, is to replace this sequence of nested intervals with just the leftmost point of each interval. Because the intervals are getting smaller and smaller, the information of the limit, whatever that is really contained by just the left endpoints. You don't really need to know the right endpoints if you know that the length of the intervals is going to 0. So we could say that we can be thinking about arbitrary monotonic bounded sequences. So now we're talking about just sequences of rational numbers which are, say, increasing, but we know that they're bounded so that there's, at least some limit. They don't just keep going up and up and up. For example, in the previous example, the A1, B1, the B1 is an upper limit to all subsequent AIs because they're all contained in the original one, so they're all less than B1. All right, so that's another way of thinking about what a real number might be. Another way of trying to set up a theory of real numbers. And this also corresponds to certain kinds of operations and analysis where we're taking limits of positive series or lengths of curves sort of fits inside this kind of framework. You get one polygonal representation, and then you get a finer polygonal representation that's going to be a slightly bigger length, and then a finer one's going to give you a slightly bigger length, and so on. The same kinds of cons as the previous one. We still have to worry about not having unique representatives. Equality is still a crucial problem. And it turns out that when you think about subtraction and division, it's not at all so clear how to define those operations in the context of monotonic bounded sequences. Okay, as a way of freeing oneself from the monotonic aspect of these ones, another variant is to think of Cauchy sequences, where we're allowing sequences AI like this, but they don't have to necessarily be increasing and bounded. They're allowed to jump around back and forth, but we don't want them jumping around further and further away from each other. We want them kind of, coming closer and closer and closer together as we go out. So they're allowed to jump around by smaller and smaller amounts. All right, so the standard way of saying that is to introduce this Cauchy criterion that for every or for all epsilon greater than 0, there exists a natural number n, so that if m and n are bigger than or equal to n, then the difference between the little nth and the little mth in the sequence is less than epsilon. Okay, it's a standard kind of Cauchy criterion. As I'm going to explain in my Math Foundation series, there's actually a logical problem with this condition, despite it being a cornerstone of modern analysis. The logical problem is that there's really an infinite number of conditions involved, because it's a condition for all epsilon. Now, in standard examples of texts, they usually give you examples where you don't have to check an infinite number of conditions to check that this works. So if you have a simple or simple-minded enough example, the infinite aspect of this doesn't become apparent. But it is possible to give examples within the usual framework where you do have to in fact check an infinite number of conditions in order to verify that a given sequence fulfills the Cauchy criterion. So there is a logical problem already with the nature of this definition. The advantage is that it's a little bit more flexible than the previous one. Arithmetic works a little bit better. You don't have to worry about the monotonicity being destroyed by subtraction or division because we're not insisting on the sequence being monotone anymore. But as before, an infinite amount of work is required to do arithmetic. One of the major disadvantages of the Cauchy sequence approach is that we lose control over an estimate of the real number that a sequence defines. Because the sequence is allowed to bounce around and doesn't have a monotone property or a bounded property, it means that we never know whether we're close or not to the limiting value that the irrational number is supposed to have. And again, the same crucial problems that we don't get unique representatives. So it's very hard to do arithmetic effectively, and it's very hard to show that two Cauchy sequences are in fact equal. One way of trying to avoid this problem of no unique representatives is to go to another variant, which is to consider not single Cauchy sequences, but equivalence classes of Cauchy sequences. All right, so this is a kind of a sleight of hand where we try to get around some crucial problem by sort of rearranging the furniture. So what we do is we try to solve the uniqueness problem by lumping all the Cauchy sequences with the same limit, whatever that means, into a single set. So we identify when two Cauchy sequences seem to be heading towards the same goal, whatever that is, and then we lump all of those into one big thing, one big set, call that an equivalence class, and then think of the real number as being that entire object. Okay, well, it does deal with the unique representative problem because now the real number is this whole big thing and it's unique at some level. But it also becomes impossible to exhibit meaningfully a single example of such a thing. If you actually are asked, well, give me an example of a real number that's defined exactly this way, where we're actually fulfilling the conditions of the definition, it's impossible to do that. And curiously, maybe amusingly, it turns out that when you look at a real number defined as an equivalence class of Cauchy sequences, lo and behold, they turn out to all look exactly the same. What do I mean by that? So consider this theorem of mine. All right, theorem in quotes. Okay. The theorem is that all equivalence classes of Cauchy sequences look exactly the same. All right, this is all an imaginary kind of thing because I'm supposing that this entire fairy tale of infinite equivalence classes of infinite sequences and so on makes sense, which I don't believe it does, but let's just play along. Okay, so here is a real number alpha, according to the equivalence classes of Cauchy sequence idea. And here's another real number, beta. All right, what is the definition telling us? It's telling us that this real number is in fact an equivalence class of Cauchy sequences. It means that here you see strips of paper. Okay, this real number is a collection of lots of Cauchy sequences, which we can imagine as being written on a long tape. So the first rational number, comma, then a second rational number, comma, then a third rational number, comma, on each one of these strips. And to exhibit this thing a little bit more clearly, I've taken one of these strips at random and I've pulled it out a little ways so that you can see some of the first entries. So the particular one that I happen to have chosen at random, pulled out, happens to look like this. So it's a sequence of rational numbers. It's a Cauchy sequence of rational numbers. It starts out 314 over 718, then minus 58 over 3004, and then this one, then this one, then this one, then this one, then this one. And at that point, I need to pull it out some more to let us see some more entries. Now if you look at this, you'll say, well, it doesn't look like a Cauchy sequence to me. Aren't Cauchy sequences supposed to look like 3, and then 3.1, and then 3.14, and then 3.141, and so on? Well, yes, that's what the examples in your textbooks would like you to believe. But in fact, if you actually pulled out a random element in this equivalence class, which defines this real number, you would in fact find something that's much more convoluted than this. This is a very simple kind of example. But my point is that if I looked around in the equivalence class for this other real number, beta, which doesn't have to be at all related to alpha, completely different real number, I can find one of these tapes. Actually, I can find a lot of them, but in particular I can find one. So if I pull it out to the same extent, I find exactly the same sequence of rational numbers as I found there. Exactly the same numbers. You might say, well, that's only because you've only pulled out the things to a certain small extent. True. But suppose I pulled this one out not just to reveal 10 entries, but to reveal 10 trillion entries. Okay? I'm pulling and pulling and pulling and pulling, so now you can see the first 10 trillion entries. I claim that I can easily find, or maybe not easily, but I can find in here a strip where if I pull it out so I can see the first 10 trillion entries, you're going to see exactly the same 10 trillion entries as you do on that one. And the reason is very simple. It's because the definition of a Cauchy sequence does not prevent us from changing the initial segment of any sequence. If this is a Cauchy sequence with a certain limit, then I can change the first 5 or the first 5 billion entries arbitrarily, and I'm not going to change the fact that this is a Cauchy sequence for that real number. That means that this collection of Cauchy sequences and this collection of Cauchy sequences are completely undistinguishable from a finite point of view. If it's just a question of pulling out the tape to a certain trillion number of places and then reading off what you have, there's no way of distinguishing this real number from this real number. The only way of telling the difference is by pulling out all of a tape. Looking at the entire tape all at once in its entire infinite aspect. In other words, playing God. Dancing with the fairies at the bottom of the garden. Isn't it great? 19th century mathematicians were not unaware of the kinds of problems that I've been talking about, because they're not that sophisticated. And they probably didn't write a lot of articles about it because people wanted there to be a theory of irrationals. Because the theory of irrationals allowed them to talk about integrals and lengths and the values of transcendental functions and solving polynomial and other equations. They wanted a theory of irrational numbers, so they did not want to think about the possibility that no such theory logically works. It was a great relief to them when Richard Dedekind, in around 1870s or maybe 1880s, finally came out with a theory which satisfied most people as being a reasonable theory of what real numbers really are. This is the theory of Dedekind-Katz. So in my view, the theory of Dedekind-Katz is actually a very subtle sleight of hand. It's a mathematical equivalent of lifting yourself up by your own bootstraps. It doesn't really work. It's a smoke screen, and it's worthwhile looking at it more carefully. And in particular asking the question, can we see some examples? How does this actually work in practice? As in most situations like this, this is often the key test that separates whether someone knows what they're talking about and just is talking about something. Okay, so Dedekind's thinking was motivated by a reasonable insight that he had. Okay, well, he was probably thinking about how does one exactly define the square root of 2. Okay, it's not enough, as he realized, to just say, let's talk about the number the square root of 2. First, we have to construct it before we talk about it. We have to define what we mean by the square root of 2. Okay, it's not enough just to say, oh, it's a number whose square is 2. Okay. So Dedekind's answer to this question is the thing that motivated the idea of a Dedekind cut. So Dedekind thought, well, the square root of 2 it's some number somewhere around 1.4. And it's some kind of thing that's sitting on the number line, but it's not a rational number. It's like a gap in the rational numbers. There are rational numbers to the right, and there are rational numbers to the left of this gap, but there's no actual rational number sitting where we would like the square root of 2 to be. And so he said, well, let's think about just the rational numbers. Think about the rational numbers which are less than what we would think the square root of 2 ought to be, and think about the rational numbers which are greater than what we think the square root of 2 ought to be. Both of those infinite sets are definable in terms of the rational numbers. So as long as you're happy with infinite sets, and at that time Cantor was developing his theory of infinite sets, and people were becoming more comfortable with the idea of working with infinite sets. So in modern notation, what we would say is consider the set capital A of little elements belonging to the set of rational numbers, which has the property that a squared is less than 2 or a is less than 0. And that is a set that I've shown here in red. So it's all the numbers whose, when you square them, you get something less than 2, or any number that's negative. You can't just have this, because then minus 5, say, wouldn't be included. We want minus 5 to be included. We want everything to the left of where square root of 2 ought to be. And similarly, we define capital B to be the set of B in the set Q, such that B squared is bigger than 2, and B is also bigger than 0. We do not want to allow minus 5 to be in B. All right, so here's the picture of A in red. Here's the picture of B in green. And now if we do believe in infinite sets, and for me this is a big if because I don't believe in infinite sets, but let's suppose that we do temporarily, then we would say that A and B partition the infinite set Q. It means that their union is Q, so every rational number either belongs to this set or belongs to this set, and they do not intersect. Okay, that's the meaning of partition. And furthermore, all the elements of A are less than all the elements of B. So if you choose any element of A and you choose any element of B, then that element of A will be less than the element of B that you chose. And furthermore, A has no greatest element. There is not an element of A which is bigger than or equal to all the other elements of A. So the left set is required to not have any greatest element. And so then Dedekind said, well, we can think about what root 2 is by thinking about it as being just this partition of the rational numbers. So more generally, we can think of a real number as being such a partition, or a cut. And now a partition which has these properties is called a Dedekind cut. And so Dedekind's solution to what is a real number is a Dedekind cut of the rationals. So this may seem rather awkward kind of thing, invoking infinite things, infinite sets to get at something like square root of 2. But it was in keeping with Dedekind's work in number theory, where he was a pioneer of the language of ideals. And this idea of sort of infinite sets playing the roles of things was something that he was quite comfortable with. And many people look at this and say, great, finally I know what a real number is. It's just a Dedekind cut of the rational numbers. A partition of the rational numbers into two pieces that satisfy these relatively simple requirements. So, does it work? So does the theory of Dedekind cuts really work as a foundation for the so-called real numbers? Well, there's certainly an advantage. So one advantage with the theory, if it works, is that arithmetic with Dedekind cuts is much easier to define, and it is possible to make some case that the laws of arithmetic can be proven in this context. Okay. So that's a definite advantage. However, The disadvantage is that the simple nature of the root 2 example is not representative. Okay, it turns out to be a rather special case, which is altogether too simplistic to properly represent what really happens. When you look at more general examples, this simplicity evaporates, and the complexity of the Dedekind cut system just reduces to the same complexity that you have with all the other systems. And that's why in textbooks where they're talking about the Dedekind cut system, they will rarely go beyond the square root of 2 example. So most students who will have learnt about Dedekind cuts will have seen the square root of 2 example and will have nodded and say, yeah, that sounds reasonable. We have a relatively simple criterion telling us whether a rational number is red or green. But, for example, to exhibit pi as a Dedekind cut is an interesting challenge. How are you going to color the rational numbers into those ones red, which are less than pi, and those ones green, which are bigger than pi? Well, what you're going to have to do is you're going to have to go back to Stevin, or some of the other variants of Stevin's approach. For example, you're going to have to think about nested sequence of intervals. So here's A1, B1. Here's A2, B2, here's A3, B3, here's A4, B4. Suppose we have a real number defined as a nested sequence of intervals, either in the sense of Stevin or the more general one. How are we going to associate a Dedekind cut to such a thing? Well, what you're going to do is you're going to have to paint the rational numbers red and green. Okay? So the first interval is A1, B1, and you are going to paint everything to the left of this endpoint, not including that endpoint, red. And you're going to paint everything to the right of this one green, including that one. Okay, so you've painted that, all that red, and you painted all that green. Okay, and then we go to the next interval, A2, B2. And you're going to paint then, take up your paintbrush again, and paint starting from here all the way, everything to the left of that, including the endpoint that you left out there before. And then here you're going to go and, starting from here, you're going to paint all that green. You don't have to carry on because you've already done that stuff. So the red and the green painted areas have increased slightly. Then you go to the next interval. Repeat. Paint that little piece red. Paint that little piece green. Then you go to the next one. Paint this red. Paint that green. There's no way you're going to be able to do this without an infinite number of operations, because you're going to have to go one interval at a time. There's not going to be a single or even a simple finite procedure, as there was for the square root case, to tell whether a given rational number should be green or red. So the root 2 example is illusory. It's too simple-minded. It does not reflect the real complexity of the situation. In fact, in the real case, in order to calculate or to exhibit a Dedekind cut for pi, you're really going to have to go back to Stevin or some equivalent thing and find out a nested sequence of intervals to approximate pi. You're not going to be able to do it without essentially resorting to one of the previous strategies for understanding pi. So it becomes a bit of a red herring, really. The Dedekind cut procedure doesn't work any more than any of the other procedures. It is still lost in the sea of ambiguities having to do with infinite procedures. Which is why most calculus and analysis texts don't even bother. Don't even bother with any of these variants, because they realize that if you, by the time you've explained them and tried to give some examples of real number arithmetic, most students would say, I don't believe this. This is too complicated. This does not correspond with what my computers are doing. This is some kind of fairy tale world, which is exactly what it is. So of all the developments in modern mathematics, say in the 20th century, probably none is as important as the dramatic increase in our reliance on computers, not just for making calculations, but also to reveal structure and understanding. And not surprisingly, the theory of computation and computer science and programming sheds a lot of light on the theory of real numbers and the challenges in setting that up correctly. So we now have insights that the 19th century mathematicians just didn't have because they didn't have computers. So these days we understand that there is an increased need to tie any theory of real numbers to a deeper understanding of algorithms. Right? The essential aspect of an infinite sequence really is that there's some algorithm or some program or some procedure that's generating it. And we really want to tie this in with an understanding and a theory of algorithms or programs or procedures, whatever that might be. If you have a theory of irrational numbers which is floating above any such computational theory, then it's probably going to get lost in the fairy tale land, like a lot of the 19th century developments were. In particular, arbitrary sequences of digits. Right? This idea of the axiom of choice allowing us to contemplate an arbitrary sequence of digits which does not have any program or algorithm or procedure to generate it, is now increasingly looking absurd for most young people. Most young people realize that it doesn't make any sense to talk about such things. It's much safer to tie sequences, infinite sequences, to actual computable sequences. Those are really the main objects that we should be considering. And future generations of mathematicians will look back on our time, so even the year 2014. It's remarkable that most mathematicians think that if you look at the interval 0, 1, okay, and you look at the so-called real numbers in the interval 0, 1, that most of them are uncomputable. The infinite digits that correspond to most numbers in the interval 0, 1 are not corresponding to computer programs. And that means that they are not capable of being written down in any meaningful way. So all the numbers that we usually deal with, pi, e, root 2, logs, integrals, sums, they're all computable. Their nature is such that you can get a computer program to generate the digits. We have no examples, or no meaningful examples, of uncomputable numbers. Yet the modern pure mathematician has this really absurd position where he really thinks that the uncomputable numbers are far outnumbering the computable ones. It's a very strange position. And so really what I'm saying is the axiom of choice is fantasy. We need a much more down-to-earth, concrete, computational approach to this challenge. All right, but there are very big challenges involved if you want to go in this direction. So if you want to create a real theory of real numbers, okay, you need to worry about algorithms. You need to worry about the question of equality at the level of algorithms. How do you tell whether your algorithm and my algorithm are generating the same sequence of digits? A huge problem. How do we find unique representatives so that we can actually do arithmetic in a well-defined manner, so that we can test and check whether an answer is actually correct or not? How do we do arithmetic at the level of algorithms? How do we prove the laws of arithmetic? These are all major challenges. And I think this is part of this problem of how to model a continuum. It's a modern version of this problem, and its difficulty is very high, at least at the level of 9, and possibly aspects of it at the level of 10. So in order to make real progress, we need a lot more insights. We need a lot more understanding of algorithms. We need to take computer science and their work much more seriously with regard to the foundations of mathematics, for sure. So I realize this is going to be a very difficult lecture for a lot of my fellow mathematicians to listen to, because it's very contrary to the current setup. It's very threatening to the status quo. It means that a lot of things have to be revisited. A lot of theories have to be readjusted. It doesn't mean that modern mathematics or analysis will collapse. It just means that a lot of things have to be rethought and new frameworks have to be developed. And we have to take a much more down-to-earth and measured approach to the foundations of mathematics. So to wrap up, I want to just make you aware of some of the consequences of avoiding the difficulties with real numbers that I've been talking about. So in the 20th century, people have sort of at some level realized the essential truth of what I'm saying at some level, okay? And as a result, a lot of people have retreated or perhaps even capitulated to a position of axiomatics, where we give up on trying to create a theory of real numbers by proper definitions and theorems and retreat to a position of saying, guys, let's just assume that certain things are true. And let's try to dress this up as being sort of at the same level as Euclid, what Euclid was doing, calling them axioms. So this is the real reason why the axiomatic approach to mathematics was so prevalent in the 20th century. This is really the core reason. It's to buttress our theory of the real numbers. That's the critical issue. Right? We want the real numbers there because we want to evaluate integrals, we want to evaluate sums, we like the idea of having solutions to equations. We like the idea of being able to convert infinite processes to numbers. It allows us to say lots of things. Okay, so, but that has also led to a growing gap between what people can actually do computationally, say between computers' evaluations and mathematicians' assertions. We're having a situation where there's been a shift from explicit examples towards abstract sophistications. So this general orientation means that we've had to free ourselves from the foundations. And so we become a little bit reluctant to spell things out with concrete examples and computations. It becomes safer to work at a level of abstraction where we're allowed to say things like, let this be that, and consider this, and take that. All right. So this weakness with regard to irrational numbers affects a general mind frame towards a lot of other related mathematics. Almost all mathematics becomes infected with this reluctance to become completely explicit and clear. So the fantasy of real numbers, we really pay a heavy price for the convenience of having explicit values for various things that we'd like to write down. For being able to believe that there really is such a thing as cosine of 5. That e to the minus 2.4 really is a number. That log 7 is really a number. That if we write down a sum like this, sum from n equals 1 to infinity, 1 over n to the n plus 1, that's actually a number. That an integral like this is actually a number. If I actually ask you, well, what is this number? Well, it becomes not something that you can compute in any real sense except to say, well, it's sort of itself. So we pay a heavy price for this convenience. And if we adopt a more realistic point of view, we have to start acknowledging that in reality, things that we write down like this are really more like what the computer scientists are telling us. Namely, they're things that we can evaluate within a given interval. And how much accuracy you want, that's up to you. You want a certain amount of accuracy, then the computer scientist will calculate this up to a certain interval. Or calculate this up to a certain interval. Calculate this up to a certain interval. And that's somehow essentially a more honest representation of what these things really are. They're not numbers, they're more complicated things, they're more things of applied mathematics that have ranges of values that depend on the amount of accuracy that you want. That's what the computer scientists are trying to tell us. So there's a lot of more things to be said about these kinds of things. I'm going to be talking about these issues at length in the Math Foundations series, and I'm going to hopefully show you there that there are really good things that arise from thinking more clearly about the foundations. It's not just negative, it's not just that we're tearing things down. So we're clearing the ground to build up a more sensible and a pleasant and more beautiful mathematics. But first of all, we do have to do a bit of excavation. All right, in our next video, we're going to look at another famous math problem, the problem of the cyclotomic polynomials and their coefficients. It's an interesting chapter of abstract algebra. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.